In this final example, we're going to look at adiabatic cooling. So again, we remember adiabatic is code for the rate of heat transfer is 0. And so we're going to cool something with no heat transfer. So it sounds like a oxymoron, right? One of those words that doesn't work together. But we're going to find that even though I have no heat transfer, I actually will see some cooling. This is the concept of how those spray misters work when maybe you're at an outdoor dining facility and they'll have little sprayers around the edge of the patio. So a method for adding moisture to air is by spraying water into the air. And assuming the air enters the humidifier, or this system, at 100 degrees Fahrenheit with wet bulb temperature of 70 degrees Fahrenheit, and the air exits at 80 degrees Fahrenheit, the process is adiabatic. How much moisture is added per pound of dry air? So again, we're going to start with, we have the dry bulb temperature is 100 degrees Fahrenheit, a wet bulb temperature is 70 degrees Fahrenheit, and we're going to have a final temperature of 80 degrees Fahrenheit. We're going to be adding water, but the process is adiabatic. So how will we solve this problem? Let's go to our psychrometric chart and see. So we've got our first system where it's 100 degrees with a dry bulb temperature of 100 and wet bulb of 70, and that intersection is shown here on the graph. We know that the air is going to exit at 80 degrees Fahrenheit. So again, that point is shown on the graph, right? So what is going to stay the same, or, well, really stay the same if I'm talking about an adiabatic process where I'm adding water? Certainly there's going to be more water, so I expect it to be somewhere, the final point is going to be somewhere up here, right? Because I've added water. But where should that point lie on this graph exactly? What's staying the same is the enthalpy. And so we can approximate that by not worrying about the enthalpy deviation and just look at the saturation enthalpy. So follow one of these constant enthalpy. That means that I'm going to follow along the wet bulb temperature lines that go at a funny little angle there because I'm looking for a constant enthalpy. Now I realize there's going to be some little bit of error introduced to this because I'm ignoring the enthalpy deviations, but the error is going to be very, very modest, and I could go back and by trial and error I could adjust for that if I wished. But if I follow this line across here and look at the 80-degree line, the one that I've marked in gray, to where this marks here, my second point will be right here. So point 1 was where we started, and point 2 is going to be where this constant enthalpy line intersects with 80 degrees C. Now, in this case, they've asked how much water do I need to add to the system? So I simply look at the moisture content. So I have my final moisture content looks like it will be right in here, about 0.0133. And the initial looks like it was about 0.088. I left out a 0.0088 pounds of water per pound of dry air. And if I subtract these, then 0.0046 pounds of water per pound of dry air need to be added to achieve this cooling. Now, if you're going to try doing an adiabatic cooler on your own, I will tell you that you are physically limited to when it reaches saturation. All right, this concludes the set of videos. I do want you to take the time to go in and look at some of the other videos that are available to you online. I have in Canvas listed quite a few of those. But this is an important topic, and it's kind of, challenging the first time. So this concludes this lesson, and our final lesson for Unit E, we're going to be looking at mixing